Hi, I'm Nehal. So, we will be taking an ongoing journey in physics, and this is one of the introductory classes to the many ongoing sessions that we'll be taking forward with. This is slightly unconventional introduction to the regular introduction that you listen in physics classes. Now, we would like to ask a question: what exactly is physics? Now, the, the question goes back many centuries, like almost 4 centuries if you think formally, but it is much, much beyond that. Like the Greeks have worried about it, the Indians have asked fundamental questions, metaphysical questions, and the history has been long back. Ever since Greeks, Indians, Egyptians, and many other unknown civilizations. But formally speaking, a regular structure for physics came up in 1600s from Newton. So this I would like to call is an edifice of physics. The picture that we have physics in the modern era in 21st century is a building upon all these scientists, all these people, all these concepts, and so on. So it is an ongoing building. I mean, many new principles have to come up. Uh, we still have to discover many unknown things in the universe. So edifice is basically a building. So, what does this building comprise of? The what is the picture? I mean, for example, let's say you capture an image. This image has to convey something to you. Now, in that sense, what exactly is the image of physics telling you? Um, as a surprise, it's the study of universe itself. It's a study of physical universe all by itself. Uh, so we will debunk one by one. I would like to propose an experiment to go through, but we'll see as we go along. Okay. So physics is a part of science, right? I mean, of course, the same principles that you have physics, it's applied everywhere in science. The question is, how exactly do we do science in the first place? Uh, is there any methodological process? And yes, there is. There is a simple 5 to 6 step rule that all scientists usually do. Um, this is called reductionism. So, I mean, let us take an example. For example, I've given you a watch. Now, I ask, uh, how does this, what is this watch? And you say, for example, it says time, that's one. And it works, there are three things in it, like a minute hand, second hand, and an hour hand, that's one. So, what all that you describe about this watch is technically a description. It is what a watch is. For example, imagine this cup. Uh, sorry, this cup. What a cup is. How do we define a cup? A cup is something which holds water. A cup is something which is used to drink. Uh, a cup is cylindrical in shape, though you have other shapes. You are not technically telling me what a cup is. In fact, all the properties of the cup. In fact, if you want to describe anything in this universe, you would start by talking about the properties of the universe. Okay. Now, this is description. Now, let's go formally more into it. Okay. Let's take up a question and try thinking upon it. Uh, Yesterday, my nephew came over, so we tried playing up with lasers. Now he has this green laser which goes really, really far. Initially, he was playing it for a while, and then a question sparked in me. I asked him, "How far does this laser actually go?" Now, this is the first step in science. You observe the phenomenon. You observe what is happening, and this is codified into a question over the process. So, what's the question here? The laser is moving, we definitely know that. And how far does it go is the question. Now, okay, how do we know? We experiment here. So we tried shooting the laser at different points. We tried different distances. We were clearly able to see it is going till 6 kilometers. I mean, 10 kilometers. If you're standing on a highest cliff and ask how long does it go, I'm pretty sure we will be able to see at least 10 kilometers ahead. And this laser is going forward. Now we started to hypothesize. What is hypothesis? You formulate an explanation for this phenomenon which is happening. Uh, we don't know what is happening. So I mean, since I have been doing science for a while now, I have asked him, okay, this is called a monochromatic laser. Now, what is monochromatic laser? It's a single colored. I mean, only it's a green laser. You can only see green, but it's not typical light that you see around every day. If you switch on a tube light, it's a white color. Now, you must have known. I mean, white color is a collection of colors. It's not one color. Now, if you take a prism or so, and and look into it, the white color is split into seven colors, right? Now, green is one specific part of this white color. So we said, okay, if I switch on the white light, tube light, how far does it go? What does it depend on? Now, this is a question which we did a couple of experiments, and this is we concluded an explanation, a hypothesis, and a formulation. Let's say an explanation of what is happening. Then we took this experiment, took this hypothesis, and tried in different cases. Then we asked a couple more questions. Uh, let's say we shoot it up to the moon. How do we know if it is truly going to the moon? Um, in fact, I mean, how do we know the light is going to a certain direction or to going to a certain point? Oh, this is an interesting question and a much deeper question. Now, I asked him, um, okay, I probed him a couple of questions and we arrived. How do we see things in the first place? We see things when light falls on it and the light is reflected off the object. For example, again, let's take this cup. I'm seeing this cup, so what is actually happening here? Light is falling on this cup and it's reflecting backwards. It's reflecting every direction, in every direction and every formulated way. But since I am looking at this direction, the light rays which are being reflected from this cup in this direction is perceived by my eye, right? Now, we can never know whether the laser is going to the moon because there is no coming back, right? So this is a hypothesis. Now, there are different ways to test this hypothesis. What do? We take experiments. Perhaps first is how long does it go, so you can shoot up at different points. Second is, does this interact? You can come up with many different questions for a particular experiment. Then is data analysis, which is a very crucial part in science. You collect data, you observe, you hypothesize, and you experiment, and then you collect your results. By seeing, there are more complicated ways of looking at this data. Data analysis is such a huge part in science, of course. I mean, now the data science is booming up everywhere. I would like to drift apart and tell you something which is interesting. In 2009, there was an experiment by CERN, Center for European Nuclear Research, which asked a fundamental question. I mean, the question is, how did the universe form? If you know the experiment called Big Bang. So we don't know, but what they did was they took a big chamber, a big vacuum chamber, and they have taken subatomic particles. Subatomic particles are very tiny particles, which is much less than an atom. Now they accelerate it with a very high velocity and they bombard it to each other. Now this is an experiment. The hypothesis is Big Bang was a huge bang. Now, how do we create a bang? You smash things together. Now, how do you smash things together? Of course, you can ask, why can I not smash two balls? You can, but the explosion won't be so big. So to simulate this experiment, what they thought was take a fundamentally small particle and accelerate it to almost speed of light, and then you bombard it, and let's see what's happening. So this collision, the smashing of particles, will be done several thousands of times, and all of this data is actually recorded, and then they conclude by seeing the patterns in the data. This is common to any scientific experiment that we do. Uh, you try to analyze the patterns in the data, and then you conclude something. You come up with an interface of what is actually happening. Now, if once this experimental results are done, you want to verify it, right? You verify it a couple of times, and then is it truly matching it with your hypothesis? Is the question you need to ponder upon. Yeah. Uh, you can do a simple experiment for yourself. Take a coin. Now we don't know what this coin is actually made up of, right? I mean, it could be any coin. Now, let's say you are tossing it 10 times. Question is, how many heads and how many tails can you have in all of it, right? Now, how do you do it? first you conduct a couple of trials. You take all of the data points. You write down all the data points. Like I have done 10 tosses and I've seen five heads or six heads or four tails. Now you vary it. I mean, now this is one set of experiment, like 10 trials is one set of experiment. Now you conduct another set of experiment, like other trial, which is again of 10 trials. So after a couple of iterations, then you draw up a conclusion saying, okay, when does the coin actually be more in heads and more in tails? Well, that is an experiment to think upon, and you finally come up with a theory, right? This is exactly what we do in science. Okay. Now, any experimental result is always given to scrutiny. For example, let's say Earth is round. I have to prove why Earth is round, and this has been questions for thousands of years, much earlier than Greeks. Now, do you know how did people actually, discover that Earth is round? So there was this person, I forgot his name, but he took a point in the sea and he started drifting. I mean, he did not move left or right, and he started moving at the same path. After I think probably a year or year and a half, he reached the same point, which is technically implying that it is a circle. I mean, let's say you're starting here and you move forward and forward and forward, and you don't change the direction, you will eventually end up with the same point where you started. What does it mean? It's a cyclical loop. It's a circle. Okay. Now, the flow of physics is very vast in structure. It's not just mechanics. It's not just thermodynamics. It's everywhere. The whole universe is just not one subject. And the strange thing about physics is it's very compartmentalized. I'll tell you what it is. For example, let's say that you want to study vehicles, automobiles. Now, to study automobiles, you might have to study fuel, but you don't have to study the molecular structure of fuel, right? So each domain of physics is very compartmentalized. For example, you're studying a specific phenomenon. These rules need not apply at anywhere else in the domain of physics. The so I hope you understand. Like for engineering, you don't need to do quantum mechanics, right? So the range of physics is very vast, from subatomic particles to vast cosmos, from electrons to galaxies. Now, next, I would like to propose an experiment which includes basic fundamental quantities which we are aware of, which we daily use to, which is mass, length, and time. Okay, this is something I want you to focus. Now, imagine we are on a bare island. There is no mathematics, no laws of physics. We don't know anything yet. Okay, the question I would like to ask is, what is the bare minimum weight? What is a minimal weight that I can weigh with my own hands, with my own instruments, with my own sensory inputs? Um, Certainly, we could hold a small pebble in our hands and say, okay, it's a certain weight, and then you can take a big rock and compare which is smaller and larger. So I'm taking a vague estimate here, which is 10 milligrams, right? 10 milligrams would be the least weight that we could make up sense. We could certainly not say 12 milligrams to 10 milligrams with our base senses. 100 milligrams would make slightly different, but as a safe estimate, we were taking 10 milligrams. So let's focus on this picture for a moment. So 10 power minus 3 is the 10 milligrams that I'm talking about. It's 10 power minus 4. Uh, what's the highest that you can think of? Probably 10 kgs. I mean, if you're truly strong enough, probably 100 kilos is the maximum, right? So 10 power 4. Now, take the length for that matter. How long can you see with your bare eyes? Just eyes, no instruments. If you're standing on top of a mountain and the weather is very clear, I would say perhaps like 10 kilometers or 50 kilometers at max, which is in the order of tens. So 5 into 10 power 1. So 10 power 4 meters, right? Now let's ask the same thing for the time. What is the bare minimum time that you can perceive? People have done many experiments on this. There are many psychological experiments you can go and check out. Can you tell a difference between a day And a season, you can certainly tell the difference between a day. And if I lock you up in a room where there is no sun, no, you know, nothing, complete darkness, your time scales will be distorted. Your sense of time will be distorted, and people have done experiments for this. So you can certainly say with seasons, you can say, okay, a couple of months have passed, right? So if you do the math, it is almost like 10 power 4 to 10 power 5 seconds, which is the order of days, right? I would ask, what is the smallest thing that we have discovered in the universe uh, with our sensory experiment? So let's start very simple. We will say the mass of an electron. I mean, this is after science, of course. What I'm trying to say is, with our bare minimum senses, we can capture a very small amount of universe. But the universe itself is, a vast conundrum of things. The scales at which this universe works is tremendous. For example, uh, the smallest particle that we have come across, let's keep it simple and say electron. Now, electron itself is 10 power minus 31 kilograms, which is 10 followed by 31 zeros, like 0.00031 zeros. That's how small it is. And what is the largest mass that we have encountered? Is the mass of the universe itself. It's the collection of stars, galaxies, planets, satellites, everything that you encounter. And probably if you factor dark matter as well, it is another 10 power 100, which we don't know yet, but it's a rough estimate. And what is the smallest length that we have probed? It's almost the size of a nuclei. It's around 10 power minus 17, if I remember. I mean, according to the modern data. So 10 power minus 17, it was the largest size that we have ever discovered. It's the size of universe itself. I mean, the length of the universe is 10 power 26 meters. I mean, length of the whole Earth is only uh, 6, 6,400 kilometers. The radius is just 6,400 kilometers. But the radius of the universe is 10 power 26 meters. Where is 10 squared and where is 10 power 26? 24 orders of magnitude. And what is the least time that we have discovered experimentally? Which is uh, of course, the transitions in nuclei itself, which is in the order of 10 power minus 22 seconds. And the largest is the universe itself, which is the age of universe, which is 10 power 13 years or 10 power 17 seconds, right? 13.2 billion years, which is loosely translated 10 power 17 seconds. Look at how vast the scales are. It's almost 80 orders of magnitude in mass, and 26 plus 14 is 40 orders of magnitude in length, and again in rough 40 orders of magnitude in time. Now, this is where mathematics comes in. We truly don't know. There was a scientist called Eugene Wigner who wrote a paper called Unreasonable Effectiveness of Mathematics. I mean, we are just apes on this planet, right? I mean, we are circling around a planet, and it has many species, and we are one among the species. And we came up with this incredible tool called math, which was able to probe the nature of the universe, which is amazing and tremendous. So, as things progressed, people have, you cannot, for example, let's take a measurement. Now, you might come up with a different unit. I mean, you might use your fingers, and I might use my toes or feet. But again, it's a very difficult way to, you know, speak to each other and how these things work. I mean, you might say a different language, I might say a different language, and there is a language communication in problem. So people have discovered we should have a standard unit, I mean, standard way of talking and thinking things. So this is called standard units of measurement or SI units, where mass is denoted, I mean, mass is represented or studied in kilograms, length is studied in meters, and time is studied in seconds. This is an important thing. So physical laws are not absolute. Like the laws of universe are not absolute. What do I mean by it? For example, take Newton's laws of gravitation. Newton's laws of gravitation, when does it actually work? Now, there are a couple, these are called axioms or they are called conditions. Uh, can I apply Newton's laws of motion to electrons? No. When does Newton's laws of motion actually work? First, the objects do not have to travel with speed of light, or at least matters with speed of light, in comparison speed of light. These are much, much slower velocities compared to speed of light. Now, this is a limitation. So you can only do, which is very good. I mean, Newton laws are very good and a good approximate. All of engineering it relies on Newtonian mechanics, but it is not good enough to study perhaps galaxies. What the laws which work here may not work somewhere else in the universe. This is the first thing we have to keep in mind in physics. The laws that you're coming up with need not work anywhere in the universe. These are called clauses. When are these working and when are these not? There are limitations to these laws that we come up with. That is why the study of physics is eternal. I mean, it will go and go and go in time because we come up with new and new laws every day, every once in a while, once we discover a phenomenon which doesn't obey the present laws of physics. Now, this is where the domains, I mean, the regime of physics comes in. For example, as we discussed, universe is in different regimes. What we are looking is a very small snapshot of the universe, right? And what the universe is much higher. So there is no logical way to think that okay, what I'm thinking is true for everywhere in the universe, which is wrong. Okay, so what is goal of physics? Now, as we discussed it earlier, it's a study of universe itself. Now, what the fund of physics is, we always let's take an ideal a study of molecules or ideal gas equation, if you know. Now, when I start talking about Boyle's law or Charles' law, how pressures and volumes are linked and how pressures and temperatures are linked. Now, all of these studies can be unified under an equation called an ideal gas equation, which is called PV equal to RT, how pressures, volumes are linked to temperatures under ideal conditions. So the whole game of physics is, can we describe this universe in a very simple structure, I mean, the simplest structure that we can. And as you might know, we physicists have this fascination called unified field theory, where we take all the known physics and cram it into one single equation. Like, can you describe all of physics from this one equation? Of course, it's a very magnanimous goal, and and the course that we're doing is a tiny part of it. But the goal is to study the whole universe. Okay. Now, there are a couple of fundamental constants in nature. Uh, I would better show this diagram. So this is called a physics cube. Okay. So what are fundamental constants of nature? So uh, if you know, there are fundamental constants of nature, fundamental units, and derived units, right? This is the constants that I'm talking about are not the units. So there are three fundamental units that you can construct the entire physics of. One is called Planck's constant, which will lead you to quantum mechanics. One is speed of light, which will lead to special relativity, and the Newton's laws of gravitation, which will lead to general relativity of the Earth. Now, this is the whole cube of physics, and we are starting at the origin, which is here, and the goal is to study the whole physics. So I hope you will join me in this grand scale of journey together. And yeah, I'm a scientist myself, so I enjoy teaching math and physics, and I hope that you will join me in this discourse. So see you soon. Have a great day.